So in the next couple classes, we're going to talk about the mechanics of the flow around the aircraft. So you have an airplane, right? You have an airplane, and you have air that flows around that airplane. And we want to know how that small particle of air that's going here, that small particle, how does that behave and what's the properties, how we can study it. And that's what we really want to know. So for that, you are welcome to pause the video and take notes. Let's just step one step back and go over the flow types. We got several flow types. We have what we call the internal flow. The internal flow is a flow, especially airflow, that stays uh, inside a tube or something. As for an example, like gas turbines, the engine. There is an internal flow there, and maybe the engines itself. We can see several simulations for internal flows, how they look like. These are done using CFD, computational fluid dynamics. And then we have external flows. External flows, a body that's completely immersed in a fluid. That's, for an example, the air. You can consider this particular example, the airfoil. And these are some computational fluid CFD models. This is a warfighter, and this is the landing gear of a Boeing 787. And you can see that we actually do this models if you want to know what the external flow looks like. In this particular course, we're going to limit our attention only to the wings, to the external flow. We are not going to focus that much attention to the internal flow because a little bit beyond the scope of the course. Also, in continuum fluid mechanics, as we spoke, just as reviewing, we have inviscid fluids, we have viscous fluids. And we talked about this previously. Inviscid fluid is one that's frictionless. So therefore, the flow is completely symmetric on both sides. You can see if you had taken a case of a sphere and then the flow come from this side, you can see it's completely symmetric and it ends in the same spot because there's no friction involved with that. Now, most of our properties of the flows that we work are viscous flows. For viscous flows, the viscosity dominates the flow. So therefore, it does create boundary layers, as we spoke about last time. And this particular case, you can see the same sphere, but for viscosity, now all this stuff, because of the boundary layer that's created, is going to start creating some points of separation, and these are wakes that are generated there. Okay, so those are two different cases in which that happens. There are two different classifications of flows. One is incompressible flow, the other one is compressible flow. In incompressible flow, the fluid engages in incompressible flow, the fluid density is basically equal to zero, and the Mach number is basically zero. This happens mainly when you're working with water, or maybe it's many of the liquids that they are incompressible. You cannot compress them. However, in our case, that we work in airplanes, we are working with air, and the air can be compressed. So we are typically here on this side of the game where we talk about the compressible flow more than anything else. Okay, so the problems that we do here is, before I move on, I want to tell what the Mach number is. So we did define the air density. We have something we call specific weight that's given by gamma, and is nothing else than your density rho times your gravitational constant. Here the gravitational constant is 9.81 meters second squared, or 32.2 feet second squared. Okay, it depends on what unit you are using. And v is the velocity of the aircraft. And remember what I told you, either I have the airplane moving, right? Either I have the airplane moving in a static air, or I model the plane static and I have the air flow moving. It's the same problem. The problem is completely identical, right? We talked about that. So that is the V that I'm talking about. The speed of sound is going to vary according to the height and temperature. And you can see that you can have different gammas because you have different rows at different altitudes. And T is the temperature. This is the gas constant. And this is a good approximation for compressible ideal gas. So the Mach number, this is the Mach number. Um, is given by this equation and is very handy. We use that to express and explain how the aircraft's behavior in compressible flow. As for an example, this is a typical subsonic aircraft. Subsonic aircraft are typically at 0.75. So at 0.75, a subsonic aircraft, you're going to see that there are no waves that take place. They're completely subsonic. And so your air basically goes from here to there and just keeps on flowing. Flows from one end to another end without any discontinuity. Like, for instance, I don't know if you're seeing what happens when there's a missile that explodes, right? Or when there is a big missile that leaves the warfighter. The boom that you hear is not when it explodes. It's actually what happens is every time you reach the speed of sound, you're going to hear one boom. If you hear boom, boom, then what happens is it has reached two speeds of sound. That's how fast the bullet is going. That's automatically going to hear that one big boom is automatic. You're going to hear it. So those booms are given by the shock waves. And what you can see is these are shock waves that are here, but these are what we call the bow waves or the booms. And you're going to see this quite often. And what happens is in a compressible flow, your plane it doesn't experience that, but it's low supersonic. That's like this particular case over here. You're going to start seeing what we call a boom or bow wave that starts forming here. But as we start increasing the speed, as Mach keeps increasing, you can see how your wake, your boom becomes more triangular shaped. Okay, so this over here is basically bigger than Mach, typically bigger than Mach 1.5. And this one be like Mach 5 on this side. This might be anywhere between 0.99 and 1.1. This is a Mach between that value. And this is a Mach that is less than probably 0.8. So that's very typical. That's a typical compressible flow and what really happens to the flow itself. Now, in viscous flow, we also talked about this last time, but just bring it to completion. When you have a laminar flow, it's a flow that's completely smooth. Okay, so it's something like this. It's very smooth, very nice, and yes, you're gonna have a boundary layer, but it's very nice and smooth boundary layer. Now, on this side over here is a turbulent flow. In a turbulent flow, you can see that the velocity is basically dependent on the x direction because it's flowing in one direction. However, the velocity becomes, when it becomes completely unstable, you don't know what's really going on because the velocity is now, is not only, you don't only have your normal velocity that's uniform, but then you have these other components, the turbulent components that are added to the equations, as you can see. See, these are the turbulent components of the equation that make the make the problem completely turbulent. Okay. Then we have what we call hydrostatic case. Hydrostatic case is basically everything that we care for in this for airplanes. Think about you only have pressure. This is the only thing that's existing. When with the fluid dynamics, we are talking about then all of a sudden you have the airfoil and you got your lift, you got your drag, you will have your thrust, and weight is basically a static problem, but yeah, you also have weight to keep this in balance. So this is typically happens for our case. This is what we study, but there are some nice important factors that we need to understand from fluid statics, what we call the hydrostatic analysis, because it really helps us understand how your gauges that are in the airplane work. Okay. Before we move on, let me just define a few things. There are several forces that act on your plane. One I call the pressure surface surface forces. If you think about your wing, if I think about your wing, and then all the forces acting on the wing itself, if you can agree with me, those forces will look something like this, right? They basically end up something like this. They're completely perpendicular to the surface at every single point, so they are pressure loads. So mainly pressure is the main event acting on the plane itself. A body force is something that moves, something that's a function of the point, and it can move. So think about this point right here has a weight, right? A weight typically is a body weight, a body force. That's what we call a body force. Here in this course, everything that we talk about in terms of weight, body force is the only way, cases that we're going to consider. Body forces are something that externally is distracting on it. Think about this. The reason behind we have an airplane, okay? The reason behind the airplane has a mass, but the reason behind I have weight, because I have Earth. If this is Earth, the Earth is creating a gravitational force that's pulling this aircraft down here. And that is what we call mg. It's something that's actually is a result of another force, another phenomena. Sometimes electromagnetic fields, for instance. The body is going to experience some forces, but not generated directly on the body. Those are like indirect forces. Okay, so that's why in our problem, weight is the only one that we would consider in this course. So this is kind of a wrap up of what, or an introduction of what fluid mechanics will actually look like. And we will do a couple of, we will start the first discussion talking about the hydrostatic fluids.